Hi folks, are you struggling with understanding the tech behind AI? Are you a bit confused or amazed how come we have such powerful AI tools today? Then you're in the right place. In this video, I'll break down the entire AI landscape into simple, digestible terms. By the end, you'll be familiar with acronyms like machine learning, NLP, generative AI, and more. You will understand what they do and how they work together. You will see that it was the convergence of these technologies and the increased computational power of chips like GPUs that made the AI today so efficient. So, let's dive in. So here is a Miro board I created with two views, a simplified one and a detailed one. Both views use mainly two color schemes, green and blue. The green one is basically for the technologies used in making AI learn from data. The blue colors signify the real-world applications of AI. Not to scare you off from the beginning, I will start with the simplified view. The basics. We have machine learning invented in the 1940s. Machine learning is the process by which computers learn from data to make decisions or predictions. Then we have deep learning. The basis of deep learning was set up mostly in the same time as machine learning. But deep learning is a more advanced form of machine learning involving neural networks with many layers, hence the term deep. These deep neural networks are inspired by the structure of the human brain and are particularly good at processing complex data such as images, sound, and text. Then there was a major breakthrough with the invention of transformers in 2017. You can think of transformers as neural networks on steroids. The most revolutionary feature of transformers was their ability to understand the structure and meaning of data and be able to do that in very large contexts. Also, transformers process data in parallel as opposed to the sequential way in classical deep learning. The transformers greatly improve three areas in the AI: natural language processing, computer vision, and generative AI. Natural language processing, or NLP, focuses on the interaction between computers and human language. It's about enabling machines to understand, interpret, and generate human language. Early concepts were set in the 1950s. If you look closer to the diagram, you can see that NLP greatly helps with the data preparation for machine learning and deep learning. Specifically, NLP reformats unstructured data in such a way that is suitable for input for machine learning and deep learning. So basically, NLP can create new data sets for learning. Also, by looking at the diagram, we can see there is like a loop between machine learning, deep learning, transformers, NLP, and then back again to machine learning, deep learning, and so on. This shows the synergy relationship between these areas. Essentially, advancements in any of these areas over the years have resulted in significant improvements in the other areas. Computer vision is a field of AI that focuses on enabling computers to interpret and understand the visual world in the same way that humans do. Early concepts were set in the 1960s. Then we have robotics that uses NLP and computer vision. Thus, they can perceive their environments, make decisions, learn from experiences, and interact with humans and other machines in sophisticated ways. Early concepts set in the 1950s. Now let's switch to generative AI, which has its early concepts in the 1950s. Generative AI refers to models and techniques that can create new, synthetic content based on patterns learned from existing data. Based on the data type that they can generate, we have large language models that focus on generating and understanding natural language text. ChatGPT is an example of a large language model. Then we have models that generate images from text descriptions. Here we have DAL-E. Music generation models that create new musical compositions either from scratch or by continuing an existing piece. Here we have TikTok's Juke Deck. And last but not least, we have the video generation models that create, edit, or enhance video content based on input data or prompts. An example is the Runway's Gen 3 model. So in a very simplified view, these are the main concepts in AI. What we cover so far is the software part, basically the algorithms behind AI. And as a very important note here, these algorithms are mostly based on pure mathematics. And then we have the progress of hardware devices powering these algorithms. Here I am referring to the GPU chips, the graphical processing units. The exponential growth of the capabilities of these GPUs had a great impact on AI development. It was the convergence of these enhanced algorithmic structures and the processing power of GPUs that enabled AI to become as efficient as it is today. So if there is anything you can take away from this video, is the information shared so far. You can also find the link to this Miro board in the description, so you can play around and use the data as you wish, or even make a board copy of your own. Now, to the fun part. For the brave and curious ones, let's switch over to the full diagram, where we will cover each of these areas in more detail. At the core of many AI technologies is machine learning. Machine learning is the process by which computers learn from data to make decisions or predictions. Think of it as teaching a computer to recognize patterns, similar to how humans learn from experience. Data requirements. Machine learning can work effectively with smaller datasets, often requiring thousands of data points to train models. It is generally suitable for structured data, where relationships can be identified through simple statistical methods. Structured data is data that is organized in a predefined format, like tables, numerical data, height, weight, sales figures, or data that can be divided into distinct categories such as gender, nationality, or product types. Structuring data is often called labeling. Machine learning often requires more human intervention for tasks such as labeling, feature selection, and model tuning. Data scientists typically analyze the data to identify relevant features and adjust algorithms accordingly. As for computational power, machine learning algorithms can typically be trained on standard CPUs, making them accessible for a wider range of applications and environments. And for the applications, we have recommendation systems, fraud detection, and predictive analytics where structured data is predominant. We have early concepts in the 1940s and key developments in the 1980s. The specialization, deep learning, which is a more advanced form of machine learning involving neural networks with many layers, hence the term deep. These deep neural networks are inspired by the structure of the human brain and are particularly good at processing complex data such as images, sound, and text. For data requirements, deep learning requires significantly larger datasets to perform well, often in the millions. This is due to its complex architecture, which needs extensive data to learn effectively and avoid overfitting. It's better with unstructured data, which is data that lacks a predefined format, such as text, like articles, social media posts, emails, image data, photos and videos, and audio data, like speech and music. Deep learning minimizes human intervention by automatically learning features from the data. The network learns from its errors through a process called backpropagation, making it more autonomous in its learning process. As for computational power, it demands more resources, often requiring powerful GPUs to handle its intensive calculations involved in training the deep neural network. For applications, deep learning is particularly effective for tasks involving complex data types, such as image and speech recognition, natural language processing, and autonomous driving systems, where understanding intricate patterns is crucial. Also used in the pharma industry to discover new drugs and healthcare for disease treatment. With its complex architecture of neural networks, deep learning is the main driver for recent advancements in AI. One area in particular which was significantly enhanced by deep learning is natural language processing, which was born much before deep learning out of the need to enhance human-computer communication. As for timeline, we have early concepts in the 1940s and key developments in the 2010s. Transformers. Transformers are an implementation of deep learning. You can think of them as deep learning on steroids. The most significant innovation of transformers was the self-attention mechanism, which allows the model to focus on different parts of the input data simultaneously. Other improvements were the ability to handle much larger contexts and to process data in parallel, which were major limitations for the older deep learning algorithms. Transformers represent a fundamental shift in how models can process and understand data. Their ability to capture complex dependencies and handle large contexts has led to breakthroughs in various fields, especially NLP and generative AI. By the way, the T from GPT means transformer. While deep learning as a whole contributed to NLP advancements, transformers were a pivotal development that accelerated the progress and raised the bar for NLP performance. For NLP, as the processed data is basically text, the most revolutionary feature of transformers was their ability to understand the structure and meaning of sentences and to be able to do that in very large contexts. Think of tens of thousands of words, the equivalent of a text-only book consisting of hundreds of pages. Applications. While transformers brought significant enhancements to the existing application of NLP and deep learning, they also added new functionalities such as easy information retrieval, the commonly used talk to phrase, such as talk to a PDF, talk to a table, or talk to a database. Advanced text translation from one language to another. Advanced text chatbots and virtual voice assistants that understand and respond to customer inquiries in natural language, code understanding and generation, advanced drug discovery and disease treatment, and of course, they are the foundation for generative AI. As timeline, we have early concepts in 2017 and key developments between 2018 and 2020. I must mention one key feature that is highly effective for both deep learning and transformers, which is knowledge transfer. Knowledge transfer is the process of applying patterns learned from one task or domain to another related task or domain. For example, in deep learning, the knowledge of a model trained on a large dataset of general medical images, like X-rays, can be transferred to diagnosing a specific type of disease, such as lung cancer, in a smaller specialized dataset of lung CT scans. For transformers, knowledge transfer is highly effective in NLP. For example, a model trained on a large dataset of general English text can be used to enhance the accuracy of a translation system for a specific domain, like legal documents. Natural language processing focuses on the interaction between computers and human language. It's about enabling machines to understand, interpret, and generate human language by both text and voice. As NLP understands human language, it is capable of advanced language analysis, determining overall sentiment, identifying entities and key topics and intent from discussions. Having such features, you may deduct NLP can also be used in data preparation for machine learning and deep learning. For machine learning, NLP is heavily used in the labeling process, converting unstructured data into structured, minimizing the human intervention in the learning process, allowing the models to learn from the data effectively, and providing huge new datasets to learn from by translating video and audio into text. For deep learning, which works with huge datasets, NLP provides techniques like word embeddings that transform words into 3D-like vector representations that capture semantic relationships. These embeddings enable models to understand word similarities by placing related words closer together in a vector space and reduce the dimensionality of textual data, making it easier for deep learning models to process and learn from large datasets. Broadly, NLP is applied in industries such as healthcare, with analyzing patient notes and extracting relevant information to improve diagnosis and treatment. In finance, with sentiment analysis of market trends and customer feedback to inform investment decisions and detect fraudulent activities. In customer service, with powering the early chatbots and early language translation. As timeline, we have initial concepts in the 1950s and key developments in the 1990s. As you can see, machine learning and NLP have their roots extending over 70 years, with foundational concepts emerging in the 1950s. Major advancements in artificial intelligence came with the development of neural networks and deep learning techniques, particularly starting in the 1980s and gaining significant traction in the 2000s. The most explosive growth in recent years has been driven by the introduction of transformer models, which have revolutionized NLP and various other AI applications, such as generative AI. This progress has been complemented by significant hardware advancements. Modern GPUs have enabled efficient parallel processing and increased memory capacity, which are perfectly suited to the demands of transformer architecture. This convergence of advanced software and cutting-edge hardware has been crucial in unleashing the full potential of transformers, making them exceptionally powerful and versatile. That is why in the last few years we saw explosive stock price increases of companies manufacturing these chips like Nvidia. That is because big tech purchased huge amounts of these chips to train their models. If you look closer to the diagram, you can see that NLP greatly helps with data preparation for machine learning and deep learning. Specifically, they reformat unstructured data in such a way that is suitable for input for machine learning and deep learning, and thus the AI model becomes even smarter. Also, NLP can increase the volume of training data by translating the existing datasets into other languages. Looking at the diagram, we can see a loop connecting machine learning, deep learning, transformers, NLP, and then back again to machine learning, deep learning, and so on. This illustrates the interrelationship among these areas. Advances in any of them have led to significant enhancements in the others. When you consider all their complementary features, especially the knowledge transfer, you can comprehend how this forms a never-ending cycle of self-improvement. Generative AI refers to models and techniques that can create new synthetic content based on patterns learned from existing data. The core idea is that these models can produce new instances of data that resemble the training data, but are not simply copied from it. They can generate data such as text, images, music, video, and more. The foundation for generative AI is, once again, the transformer. As timeline, we have early concepts in the 1950s, with Alan Turing proposing the Turing test concept, laying the groundwork for thinking about machine-generated outputs that could mimic human creativity. Then we have, of course, the key developments in 2020s induced by transformers. Based on the type of data generative AI produces, we have their respective implementations. Large language models, or LLMs, are a subset of generative AI that specifically focuses on generating and understanding natural language text. That's why the second L from the LLM acronym stands for language. The first one stands for large because the model is trained on vast amounts of text data. As examples of LLMs, we have ChatGPT from OpenAI, Gemini from Google, Llama from Meta, Claude from Anthropic, and Mistral from Mistral AI. By now, you should make sense of ChatGPT's acronym, Generative Pre-trained Transformer. Pre-trained because it was pre-trained by OpenAI on huge amounts of text data. As for the cost of training these LLMs, here is a picture that illustrates the huge amount of cash required to train them. As we can see, GPT-3, having 175 billion parameters, took around $4.5 million to train. GPT-4, whose number of parameters hasn't been disclosed officially, but is estimated in the order of hundreds of billions, took $78 million. And the last Gemini Ultra model, having been trained with 1 trillion parameters, took a whopping 191 million. For reference, the parameters are used in the training process of neural networks of transformers. The more parameters a transformer model has, the more nuanced and sophisticated its understanding and generation capabilities can become, though this also requires more computational resources, hence the increase of price. We can see here the cost increased over time, which makes sense as these models got better. So if you ever thought of training a model yourself, you'd better think twice. But if these models took a lot of money to train, it doesn't mean we have to pay much to be able to use them. In real-world usability of the model, we will use the LLM with its general info on which it was trained, and we'll inject our own specific data required by our own needs. I will go deeper on this topic on this channel, so make sure to subscribe. Music generation models. These models use various techniques to create new musical compositions, either from scratch or by continuing an existing piece. Music generation models use a combination of textual prompts, melodic seeds, musical scores, and other input to create music guided by constraints related to music structure, style, instrumentation, and more. As examples, we have MuseNet from OpenAI, JukeTech from TikTok, and Ampere Music from Shutterstock. Video generation models. These models use advanced machine learning methods to create, edit, or enhance video content based on input data or prompts. User inputs include, as I mentioned, text, prompts, images, existing video clips, audio, motion parameters, contextual metadata, storyboards, and 3D models. These inputs help guide the generation process to produce coherent and relevant video content tailored to specific needs and constraints. As examples, we have Dreamer from DeepMind, Gen 3 from Runway, Make a Video from Meta, Deep Dream from Google, Synthesia, or upcoming Sora from OpenAI. Computer vision is a field of AI that focuses on enabling computers to interpret and understand the visual world in the same way that humans do. By using digital images from cameras, videos, and other visual inputs, computer vision systems can recognize objects, faces, gestures, or even analyze scenes to make decisions based on visual data. As applications, we have in healthcare, medical imaging such as MRI or X-rays that can be analyzed to detect diseases. In autonomous vehicles, we have self-driving cars that use computer vision to navigate roads, recognize traffic signs, and avoid obstacles. For security and surveillance, we have facial recognition for access control, object tracking, or license plate recognition. In retail, we have automated checkout systems that recognize products without barcodes or finding similar products based on an image. In agriculture, we have monitoring crop health through drone imagery. As timeline, we have early concepts in the 1960s and key developments between 2010 and 2015 with deep learning and 2020s with transformers. Robotics represent the integration of intelligence behavior into physical machines. By leveraging AI technologies, robots can perceive their environment, make decisions, learn from experiences, and interact with humans and other machines in sophisticated ways. AI in robotics involves integrating machine learning, computer vision, NLP, and other AI techniques to enhance the robot's ability to perceive, interpret, and interact with the world around it. As applications, we have industrial automation like assembly line robotics, where robots can perform complex assembly tasks with precision and speed. In quality control, computer vision systems enable robots to inspect products for defects. In logistics and warehousing, robots can autonomously navigate warehouses, pack and pick items, and manage inventory. In healthcare, we have medical robots like AI-powered surgical robots that assist doctors in performing delicate operations with greater precision, while rehabilitation robots help patients recover mobility. In domestic and service robotics, we have vacuum and floor cleaning robots, delivery robots that can deliver packages to homes and businesses, customer service robots that provide information, answer questions, and assist customers in various settings such as retail store and hotels. They are also used in fields such as agriculture, space and underwater exploration, defense and security. One emerging application is humanoid robots. Using NLP, they can understand and communicate with humans, and with computer vision, they can interact with the surrounding physical environment. In customer service and hospitality, they act as receptionists, greeters, and retail assistants, providing information and guiding visitors. In healthcare, they assist in patient care, offering companionship to the elderly, and support therapeutic treatments for conditions like autism and dementia. Education benefits from humanoid robots as teaching assistants. Public relations and marketing employ them as brand ambassadors and interactive kiosks. In homes, they assist with household tasks like cleaning and maintenance, security, and provide social interaction and companionship, especially for the elderly, so that we, humans, can focus on what we like and relax, like a boss. Or at least that's the hope. As timeline, we have early robots created in between the 1950s and the 60s, with robots like Unimate, the first industrial robot, Shaky, the first AI-driven mobile robot, and Rancho Arm, the first robot in assisting the disabled. Then we have key developments coming with NLP, computer vision, and transformers. So we reached the end of the video. This is how AI evolved through time. It took the convergence of many aspects to have the powerful AI we have today, such as the advanced neural network architecture of transformers, accelerated computational power of GPUs, huge data availability for model training, and the natural synergy between areas like NLP, machine learning, and deep learning. So there you have it. Still confused? I surely hope not. And I apologize if it seemed a bit long. I know how this topic can sometimes put people to sleep. But if you found it useful, be sure to like and subscribe. And please do let me know in the comments what other AI topics you would like to see on this channel. It really helps me a lot to make useful content that you're really interested in. I'll see you in the next one.